Okay, people in the back hear me? Okay, great. So I guess we should get started. Let's continue what we have left last week. So last week we talked about we first talked about mole balance, and then we talk about different forms of the mole balance equation, including the integral form as well as the differential form. And we talk about some examples. How do we apply the mole balance equations to solve some problems, including the tank problem and the other problem. Then we introduced the concept we basically talk about the concept of diffusion and its molecular origin. Fundamentally at the molecular level, what does diffusion mean? And then with that fundamental knowledge, we were able to basically relate the total mole flux, which is total mole flux with two components. One component comes from the bulk motion. When the fluid is flowing, it basically carries all the chemical species inside of the fluid around, right? That will give the chemical species a flux. This is called the convective or advective flux. But there's also another component for the total flux, which is not due to the bulk motion of the fluid. Even if you don't have bulk motion of the fluid, there could still be mass molar flux, and that is just due to you don't have a homogeneous solution. You don't have a homogeneous mixture. There's a concentration gradient or mole fraction gradient existing in your solution, right? So at the molecular level, that means in one location in your control volume, there are more species than the other locations. So then this random walk connectively will have a random walk of the molecules connectively will have a direction, and that creates kind of diffusion. Okay, then we were able to basically derive the total mole flux. Mathematically can be written in two components. One is due to the bulk fluid motion, is basically proportional to the concentration of the species, and the average here, this is molar average velocity of the fluid plus the diffusion term, right? Then the CI can be written as xi multiplied by c, right? And we have, by definition, we have the total mole flux of every species in the solution, in the mixture, to be C multiplied by Vn, right? So if you plug that here, we can get this. Okay. Then if you sum the molar flux equation over all species, right, on the both left side and the right side of the equation, and you will find out this equals 0. Okay, for a binary system, that means just JA plus JB equals 0. Okay. So now we have this mathematical form to relate the total mole flux with the advective molar flux and as well as a diffusive molar flux. Then we can just plug in this equation into the mole balance equation, right? So both in the integral form and the differential form. So we know that in the integral form, so we have the mass accumulation that equals to the summation of the net flux plus net reaction. Now, the net flux is basically the surface integral of the total molar flux over the whole surface of your control volume. Now, if we replace the total mole flux with these two components, and this term will break down into two terms, right? On the left, we have the left flux into the control volume due to bulk fluid motion. On the right, we have the net flux into the control volume due to diffusive flux. Okay. Similarly, we can do this with a differential form, right? You can just plug in the equation for Ni into this equation and then break this into two components. Okay. And for a binary system, we basically introduced the Fick's law, which describes basically how for a binary system, how the diffusive flux is related to the mole fraction gradient, right? Or that this is for a three-dimensional case. And if for a one-dimensional example, then this is basically the gradient will reduce to the derivative of your mole fraction with respect to your chosen coordinate, right? Typically for 1D problem, we use Z to describe the location we're interested in. And now again, if further the overall concentration does not dependent on the location Z, right? It's not a function of Z. Most likely it's a constant, then we can just plug this number into the derivative. That will give us minus dAB, right? So we have dxa multiplied by c dz, right? So then this dxac is just dca, okay? That give us an even simpler version of the of the Fick's law, Fick's first law. Now let's look at some examples. How do we apply the equations we just learned to solve some real problem? So first example we have here is to basically, it's kind of similar to the problem we introduced at the beginning of our last lecture, where when we introduced the concept about diffusion, right? So here we have two bulbs that contains species A, right? Let's say on this side, I mean, this is like we have a binary system, you have species A and B. Let's say on this side we have B, right? But now let's just not consider B, we only consider about A. We know the initial concentration of A in both bulbs, right? And we assume that in the bulb, and these two bulbs are connected by a very narrow tube, right? In this case, this narrow tube can be, can be approximated by a 1D tube, right? So you only need to consider one dimension in the Z direction. So assuming in both bulb, the mixture is well mixed, which means in the bulb, there's no concentration variation. So you have a uniform concentration in both bulbs. So then we define the geometry, right? We lay down a coordinate. We define this to be where the origin is, and this is the length of the length of this tube is L. So we have on the right hand side coordinate to be Z equals ZL. Then let's say on the left hand side, at Z equals 0, we have initial concentration to be XA dot, not XAA 0. And on the right hand side, we have XAL, right? So again, if we're talking about the diffusion problem we introduced in the beginning of our last lecture, then XA0 would be 1 and XAL would be 0, okay? But here we just make it more general. Now, further, there's no reaction inside. There are some more assumptions. There are no reaction inside. Then temperature and pressure are constant, right? So we're dealing with a very simple system. Composition are known at the domain boundary Z equals 0 and Z equals L. Now, how do we find out the flux of A through the tube, right? So I mean, initially, let's say if there's a wall in between in the tube that just separate the left side of this this control volume with the right hand side of the control volume, right? Then let's say at t equals 0, if we remove this wall, then we know there's gonna be diffusion happen. There's gonna be flux happening inside the tube that will mix the mixture in the bulb A with the mixture in bulb B, right? And how do we know what is the flux of A through the tube, right? Now, to do that, we can just start from the mole balance equation, but now with the with an extended form of the total mole flux, right? We write it down. Now we've made some assumptions that will help us to simplify this equation. First, there's no reaction, so this term vanishes, right? Second, because both temperature and pressure are constant, that means there's no pressure gradient, which means there will be no driving force for fluid flow, right? In other words, there will be no bulk fluid motion. So Vm is 0. So that term just help us to cross out this term. That leaves us these two terms. Okay. Now, if we still keep this term, then we need to solve a ordinary differential equation, which in theory we can still do that. But now, at the first thought, we ask ourselves, maybe we can start from something even simpler, right? We start from, when you solve a problem, always start from the simplest case, then work your way up. So add complexity a little bit each time, then a very difficult problem will become not so overwhelming. Here, what we are going to do is we're going to apply a pseudo steady state assumption, right? What does pseudo steady state assumption mean? Now, if we look at this, geometry, we can probably, we can write down we can draw a schematic just to describe the concentration of A in the tube, right? This is Z, and this is a L. This is Z equals 0, right? Let's say if this is a CXA, this is a mole fraction of A, right, in the tube. And we know initially there's a wall separating the left side of the tube with the right-hand side of the tube. So you're gonna have and before we remove the tube, let's assume the system is already in a steady state. That means concentration will be the same in the left-hand side and in the right-hand side, right? So this is gonna be XA. Right? Since this wall is, not permeable to your chemical species A, that's why we can maintain such a huge mole fraction gradient on both sides of this wall. And since we assume the system is in not steady state, in equilibrium, there will be no concentration gradient on both left-hand side and right-hand side, right? Otherwise, your system is not in equilibrium. Now, at t equals 0, we remove the wall. Now there's a huge concentration gradient across. And we can basically expect, A will move from, species A will move from left to right. That will create some flux just to bring the species A from left to right, right? So what we can expect is we're gonna experience some kind of like concentration gradient, concentration profile evolution over time, right? Let's say this is T equals T1, and further, sorry, this is not so, it's supposed to be symmetric, but my drawing here is not so symmetric. Let's see if I can redraw it. Okay. So at another time, maybe, we're gonna have something like this. This is T at T2. Okay. Right, so in infinity, right? It's going to reach a infinite time. It's going to reach a new equilibrium or new steady state. But now, what pseudo steady state means that, let's look at very small time variation, right? So maybe from T1 to T2, there's already a lot of time that has passed. But what if we only look at a very small time change from T1 plus delta T? Delta T is, is much smaller than T1. Okay. So in this case, even though there's flux, concentration are changing, but because delta T is so small compared to T, right? Then the concentration profile change is so small, we can just assume dt over dc over dt is just negligible, right? It's not zero, but it's so small and it's close to zero. So just allow us to make this assumption, say this term is zero. Okay, this is just for the convenience that we can even simplify this problem. Now, with that assumption, the problem becomes not so overwhelming, right? It actually becomes quite easy. There's only one term left, which is a diffusive flux. We just need to now. This is the integral form of the mass mole balance equation. What we have left is the integral of the diffusive flux, over control volume. Now, what we need to do is just define the control volume. Then we can just further break down this integral into some manageable terms, right? Since we're concerned about the mass flux in the tube, we're gonna choose the tube itself as the control volume, right? Let's say if we draw the control volume to be this, okay? So that's our control volume. Then there are basically, three portions of the control volume. We have two ends, and we have the wall, right? Now, the tube side, we know it's impermeable to the species. So, and the flux through the wall will be zero. Then the integral of J diffusive flux, with respect to the wall of the tube will be zero, okay? And then we have the two ends of the tube, left end and the right end, right? Now in this equation, we need to take the dot product of diffusive flux with the unit normal vector of the control volume, right? So we need to define the direction first so that we know how to do this dot product. So here on this surface, right, if we assume, and first of all, let's look at the unit normal vector, right? Because our coordinate points toward right. But when you define control volume, the unit vector always points outward, right, from your control volume. So that means this vector needs to be this, right, pointing outward, right? And it has the opposite direction of our coordinate. So we can write it as, minus z hat. Z hat is the unit vector pointing to the direction of your coordinate, okay? Similarly, on the tube face at this, at z equals L, your unit vector needs to point outward, right? But in this case, its direction is basically the same as your coordinate, your unit vector of your coordinate z. So it's, z hat. Now the flux. Now let's worry about the flux. Then this is where we need to make assumption, right? Let's say if initially we have higher concentration on the left-hand side, let's say if XA naught is larger than XAL, then that means, we have higher concentration at the left bulb, we have lower concentration at the right bulb, then overall flux will happen from left to right, right? So our JA I'm just gonna write it here. Right. So JA will be in this direction. Similarly here, it's the same. Okay. Okay, now we get a sense about the direction of the unit normal vector of our control volume as well as the flux, right? The second thing we need to do is that we need to consider about now in order to do this, integral, we need to know how JA dependent on S, right? Because JA is an integrand, and we are integrate it over this the two ends of the tube, right? And we know J is a function of S. Here, what is useful is that if we assume the tube is very narrow, we can just ignore the variation of JA over the S, right? So in other words, JA is a constant that allows us to, kind of like compute this integral to be, say that's kind of the cross-sectional area of the tube multiplied by JA 0, right? JA 0 is flux here, and the JAL is flux here. Okay. And this negative sign comes from the fact that JA, the direction of the JA is different from the unit normal vector A here. They are opposite directions, so you have to assign, by the rule of dot product, you have to assign a negative sign. Okay. Questions? Okay. Then similarly, right here, because the direction of the unit normal vector is the same as JA, then you can just multiply them. Now, because we have this term, all these three terms, the accumulation term, convective flux, and the reaction all vanish. We have only this term, and this term can be broken down into these two terms. So what we left is, the summation of these two terms, right? AC JAL minus this equals 0. Then because the tube cross-sectional area does not change, we can just, it's a constant, which we can just, cross that out. That will give us this JA naught equals JL, right? Which means that the flux entering from the left bulb entering the tube will be the flux on the right-hand side of your tube, leaving the tube, entering the bulb on the right, right? Further, if we look back this whole process, right, it's kind of like the way we define the control volume is kind of arbitrary, right? We choose, in this case, we choose a whole tube as a control volume, but you can definitely do this. For example, you can only choose a segment, of this tube as a control volume. And you can do the same, and you will find out, let's see if this is Z1 here. This is Z2 here. And if you go through the same process, you will find out JA at location Z1 is going to be the same as JA location J2, right? And even further, because J1 and J2, we pick them, Z1 and Z2, we pick them arbitrarily, which means that it can be any location in the tube, which means in order for this equation to hold, then basically J as a function of Z, right, is going to be a constant. It's going to be equal to JA and JL. Okay. So which means that, basically the diffusive flux is constant all throughout the tube, right? You can get this conclusion from the differential form of the mole balance equation as well. Now, what does this implicate, right? What does this mean? So we figure out the flux, but we don't know the concentration of A throughout the tube yet. Maybe we can do something about that, right? So here's what we're going to do. So start from here, right? So the total mole flux NA, we know equals two parts. This is a convective part, that's 0 because we do not have bulk flow plus the diffusive flux. And the diffusive flux can be, by using Fick's law, can be related to the gradient, I mean the derivative of the mole fraction in z direction, multiplied by the concentration and the diffusivity. Okay. Now we know Ja is a constant and C is a constant. And DAB, and if we assume DAB, the diffusivity does not dependent on concentration, it's also a constant. And what we have here is basically kind of like a ordinary differential equation, with one unknown, which is XA, which is the mole fraction of A, and one kind of like a coordinate Z, right? So, I mean, if we can solve this differential, ordinary differential equation, we should be able to, correlate, we should be able to find the relationship between mole fraction XA and how it depends on the location, right? In theory, and mathematically speaking, now we have this equation, we should do that. Now, how do we do that? I mean, what is left is just solve this equation mathematically. In order to, so again, whenever you have an ordinary differential equation, if you want to solve it, ask yourself first, ask yourself, two things. I mean, in theory, there are two ways to solve it, right? Either numerically or analytically. Analytically, if you want to solve it analytically, then typically this ordinary differential equation needs to be simple enough so that you can separate the variables, right? Because we have dxa and dz, these are two variables. We need to be able to separate them in order to do integral. If we cannot do that, then you can only solve it numerically. If you want to solve it numerically, then you should ask yourself, do I have the boundary condition? Okay. Now let's try if we can solve it analytically first. From this, what we can do is that first thing is to separate the variables. We can just take dx on right hand side and keep everything else unchanged. Okay, it seems like we can separate these two variables. Then what we need to do is just to do integral, right? Because just integral this the left hand side of the equation, the right hand side of the equation, right? Now let's do the integral. On the left hand side, when we do the integral, we need to know the range of the variable z. Right? Z is our coordinate. In our problem, it can only change from 0 to L, right? But now, if we are interested to know a function, if we want to solve not only a point, we want to solve a function, then we're going to keep z here, right? Z is a variable. Then on the right hand side, similarly, you just do the integral, right? Minus c dab dxa. Xa at location 0, it's xa 0. And at location z, it's xa z, right? Which is unknown. We don't know. That's something we need to solve. Now we have this equation. Next thing you ask yourself is, can we simplify this equation, right? That requires us to look at the dependence of NA on Z and dependence of this on XA, right? Luckily, from our derivation previously, we know NA equals JA, right? Because there's no convective flux, which is a constant throughout the tube. That gives us great convenience when we do integral because we can always take a constant out right? On the left-hand side, we have NA integral this, right? On the right-hand side, C is a constant because it's only if there's if there are no reactions, then C are supposed to be constant, right? Because you're not creating new species. Then DAB, now we have to assume DAB, the diffusivity does not dependent on concentration, because we know when you have flux, there will be a concentration profile in the tube that's going to change over time, right? And if we have to deal with the diffusivity's dependence on concentration, then that's going to be a mess. But now for simplicity, let's just assume it's a constant. Then now similarly, we can just take them out. Okay. Okay. And the rest is just simple, right? You know how to integral, this and this. It's just mathematically, it's this is just z. I mean, z minus 0, right? But z minus 0 is z. On the right-hand side, you have minus c dAB. XA, z minus XA. Okay. So we have to further simplify this a little bit, right? Let's do it here. Right. Now we just need to rearrange this equation, right? In this equation, XAZ is unknown, Z is the location. We just need to modify it a little bit. XAZ equals XA node. Okay. Then minus NA CDAB. Okay. That says, again, examine this equation. This is unknown. This is the coordinate. All the other variables are basically constant. All the other parameters are constant. This is basically a linear equation, right? So mole fraction of A is linearly dependent on Z. Okay. And if you plug in Z equals L here, right, that will give you, this. This you can just rearrange it, you will get this. Okay. Okay, I think I'm ahead of myself. We just solve it here. Okay. Now, okay, I guess we are missing something here. Yeah. So we have XA to be a, okay, okay, so I think we can further simplify this equation. Now, we have this equation, but we can actually further simplify this equation because we don't know NA, CDA, right? Even though they are constant, we don't know them. What we know is we have the concentration of XAL at the right-hand side, which we have not used, right? What we can do is just, plug in Z equals L into this equation, right? You get, let's see, so I'm gonna write it here. XAL equals XA0 minus NA CDABL. Okay, so this is, let me write it right. Right. CDABL. Okay, it's kind of slow. Now, we know XAL, we know XA0, we know L, right? So what we don't know is this. We just need to, manipulate this mathematically a little bit. Then we will be able to get minus NA CDAB. This term with the minus sign equals. So what you need to do is just, take XA to the left, XAL minus XA0, divide L. Okay. So now we kind of, although we don't know NA, we don't know C, we don't know DAB, but we figure out a way to correlate them to something we already know, or that's already given in the problem. And you just plug in this here back, right? So then this equation becomes XA no minus okay, minus XAL XA0 multiplied by Z. Okay, good. And that is basically what we have here. All right, that's this equation. Okay.
Sorry, it was really jumbled on that last slide.
Yes. Which part?
All of the right-hand side.
Yeah.
Where you're like, if you go to the next slide.
Yeah.
Where we're actually solving for this, could we?
Yeah. So
clear?
so the whole problem is that we're trying to solve mole fraction of A, which is XA, as a function of Z, right? Which is our coordinate. We know diffusion is happening in the tube between the two bulbs. So the concentration of A is changing, right? Now with the steady state assumption, we need to know how does the mole fraction of A, change with location, right? So in the end, we just need to find out how does XA dependent on Z, right? That's what we are trying to. Okay, let's review this a little bit, right? So let's just review the whole process. I know I'm probably going too fast. You get lost. Let's see if I can change the color of the pen. Know how to do that. Okay, let's just trying to change the color of pen, but I don't know how to do that. But let's just review this whole process. We start from the Fick's law, right? In Fick's law, basically, we link the mole flux with the dxa, that's kind of the mole fraction, which is unknown, with the location dz, right? And now, like I said, we're trying to solve xa as a function of z, and it seems like this gave us a good start, right? Because now Fick's law basically mathematically becomes a ordinary differential equation, with dxa and dz. And we just need to solve this ordinary differential equation, so we will be able to get xa as a function of z, right? Conceptually. Now the question becomes, how do we solve this differential equation, right? What do we have? And now that's what we examine this equation. We found, first thing we ask ourselves is, can we separate the variable, right? So like I said, differential equation.
I found this on the web for can you Fick's law of Etsy flux, whereas it saw that's kind of the mole fraction.
That's Siri spying us. So let's come back, right? So first thing you ask yourself is, can we separate variables? If so, then you can do it analytically. If not, then you have to do it numerically. And the answer for this problem is yes, we can separate the variable, right? You can just remove dz to the left-hand side and leave the dx on the right-hand side, right? Then start from here. What we do is basically try to analytically solve this differential equation and find out the relationship between xa, which is the unknown, and xa is a function of z, right? Xa depends on the location, and And XA, we try to find out how XA depends on location Z. Okay. So, I mean, up to this point, we already solved this problem mathematically. But another problem becomes, okay, now if we want to make a plot, we don't know NA, we don't know CDA. Like these are, although they are constant, but we don't know, we don't have this, we don't have the value for these constants. Okay. Now we have to go back to the problem and ask ourselves, okay, are there other conditions we have not used? And turns out XA at Z equals L, XA L is known, but we do not use this condition, right? Then mathematically, what you can do is we can relate NA divided by CDA with XA, right? What you need to do is just plug in Z equals L and compute the mole fraction of A at location Z equals L, right? By doing that, you have this equation, right? You link XA L, XA 0 with the geometry of the tube L and this whole, bulk parameter. And we don't have to break them down. What we need to know is just, connectively, they can be computed by this. This is basically the kind of concentration gradient all across the tube. You have the, mole fraction of A on the right of the tube and mole fraction of A on the left of the tube, right? That gives you the difference of the mole fraction divided by length, right? These are known. That help us basically to convert this into something known from the problem statement, okay? Then we can just convert this whole equation to XAZ equals XA naught minus this term, okay? I hope that's helpful. If not, I mean, welcome to come to the office hour, so.
A couple of questions. First off, is n equals 0 because the molar flux to the left is the same as the molar flux, right? Is that where that came from?
What's the first part of your question?
So n equals 0, it's like in the middle on the left of your board. You have like NA equals x times n. You have n equals 0.
Talking about no convective flux.
I mean, this part?
Right below.
Oh, this part. Oh, yeah, n equals 0. That's because, I mean, if you break down this equation, this is total mole flux of A equals the convective mole flux of A plus the diffusive mole flux of A. And the convective mole flux of A equals the mole fraction of A multiplied by the total convective flux of A plus B, right? For a binary system. And we know that there's no bulk flow. So that then in the whole system we study, then the total mole flux should be 0, right?
If there wasn't a force flow, then that was not.
Yeah, yes. If there's flow, then well, not be 0.
Another question is, how do you get, like, in that box equation, it just makes sense, then below that, you have it multiplied by C over L. Where is it divided by L?
Oh, so that's from here, right? So, sorry, this is a little messy, but I mean, go back to, I'm gonna keep the annotation. So after class is done, you go over this by yourself, you'll figure it out. So what I'm doing here is basically, I hope I can change the color somehow. See. Yeah. I don't know how to change the color. Okay. And then now I'm triggering. Okay, that's fine. Okay, now surface is also spying on me. Now, what I'm doing is basically, in front of Z, you have this, bulky term, which although they are constant, we don't know it. What we are trying to do is just replace this bulky term with something we know, right? Which is here. Gosh, how do I turn this off? Okay, good. Which is this? Make sense? Then that's where you introduce L. Z is still there.
Okay.
Okay, good. Okay, good. I guess we have one more problem, but we don't have the time today. We'll continue in our next lecture.